Lecture 2.3, Heat Interactions. Heating is a form of energy transfer. Defined as the workless transfer of energy. By either adding or removing heat the first law shows that the internal energy can transfer either as work or heat and change the internal energy. So what we're going to do here is that we're not interested in working here. Our goal here is to focus on heating. So then this begs the question, how does K micro change when heating is done? So before we get to that question, what we should really talk about is, why is heating and working on the same footing? The equivalent of working and heating was first realized by Joule in 1840. His famous experiment raised the water's temperature by the same amount. Using two different methods. So what he did here is he had a container. So let's say that here's my container. And what he put in one of these containers is he literally had a paddle system. And what he did here is that in this paddle system, he had a way of rotating this paddle. And this was placed in water. So the paddle is doing work. In his other experiment, he took the same container, but this time he had a heat source. And so from this heat source, we can clearly see that there has to be a transfer of energy from the heat source into the water. So what we found here is that in this situation, the work changed the temperature by 1 degree Celsius. Here, the heating changed temperature by 1 degree Celsius. So here on the left, we have a work interaction, and on the right, we have a heat interaction. Since the change in internal energy was the same for each transfer, that implies then the internal energy was changed by either working or heating. And as a consequence of this, we could see here that working and heating are on a one-to-one footing. So in other words, if I do something like this, like a little flow chart, and I say this is a one-to-one footing, then I imagine that I can flow in either direction. And then this would be my heating. In other words, they're the same process, right? They're the same process. They do the same type of thing. That's what I mean when I say on one-to-one footing. So now let's go look at that. So now that we see this, the heating mechanism has the ability to add or remove heat, which changes the microkinetic energy. So the heating mechanism has the ability to add or remove heat. Which changes K micro, right? It changes it. So if I'm going to give some type of overview of what I'm actually looking at. So if I add heat, and this word gets tricky here, because adding heat and removing heat is still considered heating. So, but I'm going to use these words differently. If you add heat, I'm going to say that you're heating. If you remove heat, I'm going to say that you're cooling. And again, that language can get really slippery. And if I'm heating, I'm going to say that I'm going to increase K micro. And on the other hand, the cooling is going to decrease K micro. Now, I should be really, that when I make this statement here, I mean, it's more complicated than this. And you'll see that in the next chapter, or not in the next chapter, later on in this chapter, we have the heating that I'm talking about right here is called specific heating. But there is a different kind of heating called latent heating. So just note that it's more complicated than this, but for here, we just want to get through the basics. So let's look at that. So now what we're going to do here is that I'm going to say we're going to look at heating to increase K micro. And so if I was being very careful, I would call this specific heating to increase K micro, but I'm not. So the first thing that we want to do here is that we're going to place a hot source underneath a piston. So what do I mean by that? So let's go look at this. So if I look at my piston, here's my piston. And so I'm going to have my piston head. And where I have my piston head then contains a gas, or ideal gas. So now I'm going to come in and I want to put my heat source right here, my hot source. So I know here that this is, of course, hot. So what I'm going to see here is that heat is going to come from the hot plate into the gas. And the reason why that is here is that the hot source is a high energy, and the gas here is at a low energy. So therefore, the direction of heat flow is then going to go into the gas. Now, let's go through the details here. Okay, so let's go through the details now. So the first thing that I would say here is that heat transfers into the gas. So in other words, we have positive heating, which then tells us that Q has to be positive. Now, what happens here is that there's now an increase in temperature. And because there's an increase in temperature of the gas, then that tells us that the change in temperature has to be positive. As a consequence, positive heating increases K micro. In other words, the fact that I have positive heating, I now change the internal energy of the gas, which of course changes K micro, and that is positive. So how do I look at this thing in terms of pictures? Well, I have a systems viewpoint. And what I'm seeing here is that here's my gas. And what I know here is that in the initial state of the gas molecules had a low average velocity. After the interaction, they end up having a higher average velocity. So now what caused it was the influx of heat into the system. That's what I mean by positive heat. And so if I look at this thing, I now have heating that's occurring. And what it does here is that it changes K micro, and then it increases it to a higher level here. And the reason why that happens here is because we had heating occurring. The bar diagram is where it really comes out really clear. So if I look at a bar diagram, I see here that I have some amount of microkinetic energy. And I know that I just increased my microkinetic energy to a higher value. So when I'm looking at this, how did I change that kinetic energy? Well, the way I changed it here is that I did positive heating. It was this heating that is responsible for the increase in kinetic energy, right? So when I look at this bar, this clearly shows increase. The heat doesn't disappear, it reappears as K micro, right? So the heat doesn't disappear, but reappears as K micro. And is that the amount that actually changed it? Now let's get to the physical explanation here. So why did the kinetic energy change? So what we want to do here is that again, we'll do this in steps. So what I'm going to do here is that I'm going to model atoms and molecules using a naive spring model. So what do I mean by a spring model? Well, what I imagine here is that I have a nuclei. And when I look at my nuclei, it has a series of electrons that are attached to it. And the way these electrons are attached is by little springs. And what you're seeing here is that these springs right here, what they do here is that these guys are the electrical potential energy bonds. That's what connects the electrons to the positive nucleus. Maybe I should have said that this was the nucleus here. And then what you're seeing here is that these guys are the electrons. Now, it turns out that that's too much work to draw. So the way I'm going to draw this is that I'm going to imagine that I have a nucleus. And then instead of drawing little springs, what I end up doing here is that I just draw straight lines. And so these represents the bonds. Now, if you look at a material, and we're going to be looking at a pot, a metal pot, materials have a lattice structure in a 3D arrangement. Uh-oh, I'm going to move this over here. Of molecules, or maybe I could say both, of atoms / molecules. And so when I draw them, here's what I'm going to imagine here. I imagine here I'm just going to draw a simple lattice system, just a 3 by 3. But these things are numerous. So I imagine that these guys, instead of thinking about one, I have a series of atoms that are connected to each other. So what I want to do here is that I want to look at the transfer. So we want to look at we want to look at the transfer of heat between a hot stove to a metal pot and to a hot pot to the water. So in other words, I want to heat up water. So if I want to heat up water, what am I actually looking at here? Well, I need some type of picture. So let's look at this. So up here, what I'm going to have here is that this is going to represent my pot. Okay, so this is the pot. And inside the pot here is, of course, the cold water. Ooh, that's not the pot. Sorry. That was my mistake. So here's our cold water. The pot is going to be the green lattice structure. So what I'm going to draw here is that I'm going to say, okay, here's me, my lattice structure of the metal pot. So if I start to look at this thing, it's going to look something like this. And this represents the lattice of the metal pot right in there. So then next, what I have here is that I need my hot stove. So here's our hot stove. So now what happens here? What happens here is that the hot stove has high energy. The pot and the cold water are at low energy. So what I'm going to see here is that there's a transfer of energy from high to low energy. From high to low energy. There's a transfer of heat from high to low energy. So let's break this down. By the way, what I'm going to explain here is called conduction, which is a process of transferring heat. So the first piece I'm going to look at is I'm going to look at the hot stove to cold metal pot transfer. Okay, so when I'm looking at this, what do I see here? For starters here, the molecules, and now I should be careful here. So when I say the molecules, I'm thinking standard heating, like an electric or a gas heater, whatever you want to call it. And these, the molecules of the hot stove have higher internal energy. What that means here is that they oscillate / collide with lower internal energy metal molecules. In the first row. So let's be careful here. So this is the first, this is the second, and that's going to be the third. So I'm thinking that I have a 3-layer lattice structure. So now that I have that, now what's going to happen is that I get like a ripple effect. And what do I mean by this? This transfer of energy causes the first row metal atoms to excite. What do I mean by excite? They now start oscillating with higher energy. Okay? And so what happens here is that now a ripple effect occurs. So now the excited first row transfer energy to the low energy second row molecules. And then we have the same thing. So then the excited second row molecules transfer energy to the low energy third row molecules. That's what I mean by the ripple effect. Now, the pot is in an excited state of higher internal energy. So now you have a pretty good idea what's going to happen next. The process repeats. The hot pot to cold water transfer. So in this case, now we follow the same the same process. So now the higher internal energy metal molecules interact. And what do I mean by interact? It forces collisions and transfers energy to the low internal energy water molecules. And of course, that increases K micro, or K internal. Then at some point, the water's average kinetic energy is high enough to cause boiling. Therefore, heat transfer increases microkinetic energy. So now this shows that heat transfer increases microkinetic energy, which is also the change in the internal energy. So now what I got to do here is that I just got to do the other half. So what is the other half? So now what I'm going to look at is I'm going to look at cooling decreases K micro. So now I'm going to do the same thing that I did before. So what I'm going to do here is that I'm going to place a cold source under a piston that contains a hot gas. So picture-wise, I'm seeing something like this here. So I have my piston, and my piston head, and I have a hot gas inside this container right here. So now underneath it, I have my cold source right here. And so what's going to happen here is that in this situation, we see that this is the high internal energy state. And then right here, this is the low internal energy state. So when I look at the flow of heat now, it always has to go from the high to the low. So now we're just going to repeat the process as before. So now we're going to, let's go through the steps. So what do I mean by that? So first of all, I'm going to see that heat from the gas leaves the piston. And when it leaves the piston, we call that negative heat, which we then write as Q less than 0. Now this causes a decrease in temperature. And that's because I'm talking specifically about specific heating. And as a consequence, of course, there's a decrease in temperature But what happens here is that this now causes a decrease in K micro. Why? Because I know that the heating here is negative, and heat changes internal energy, but that's negative. So therefore, that tells me that the change in K micro is also negative. So to connect this with the picture, I could come in and do the same thing that we did before, and we have a systems viewpoint, and we have a bar diagram. And so what's going to happen here is that if I look at my system, what I'm really seeing is that I'm seeing this here. Here's my contained gas. And what's happening here is that this gas initially has a high average speed and then a low speed afterwards. And the reason why it decreases is that there's a transfer of energy out of the system. And so what I'm seeing here is that this guy is decreasing the microkinetic energy to look something like this here. And where it really comes across strongly is the bar diagram. So if I look at my bar diagram, I know that I have to have a decrease in microkinetic energy. So when I'm looking at this thing, the only way I can do this, if there's a reduction of kinetic energy, and we see that this reduction clearly shows that this is negative heating that reduces K micro. That picture, in my opinion, is the strongest way you can see it here. Now, let's talk about the physical explanation. So if I look at the physical explanation, what I'm going to do here is that I'm going to go back up and just grab this guy, because this is really what I want to, instead of redrawing this picture, I'm going to copy this, and then I'm just going to modify this picture. Okay, so let me modify this picture here. So what I'm going to see here is that I have to reverse this now. So now what I'm finding here is that over here, in this situation, I have my hot gas, right? So here's my hot gas. And down here, let's say that this turns out to be, let's say, a cold stove. Oops, not spelled right. And so clearly the hot gas is a high energy. This is a low energy. So therefore, my heat transfer has to go out. So then what I'm seeing here is that to remove heat from a gas, we follow the same process as with heating, let's say, water that we did before. So what happens? The hot gas interacts with the metal of the piston, and it starts to oscillate the first row. And then with that, you then get the ripple effect that goes through the metal. But that means that there's a reduction in kinetic energy of the gas, and you're transferring this to the cold stove. So the process is identical.